And the last idea with proof we want to look at is this idea of using graphs and inequalities. And we talked a little bit about that. I guess the first type of one we saw was way back when we were doing these type of questions, the graphical way of solving an inequality where there's a pro-numeral on the denominator. Now, I'm not suggesting you would go this way unless you have a very accurate graph. What does x squared on x plus 2 look like? Well, it's the line y equals x plus 2 divided by that parabola x squared. So I know that there's going to be a vertical asymptote there at negative 2. On the left hand side it'll be negative because you're multiplying a positive with a negative, but then the rest of them are going to be positive. There's going to be an oblique asymptote. If I did my polynomial division, I could see the oblique asymptotes at x minus 2. Got to bend towards the asymptotes. I've got to stay in those shaded regions. The curve looks something like that. We're saying, when is that curve below the horizontal line y equals 1? Now again, you need an accurate graph. Unfortunately, I do have an accurate one here, and the answers happen to be nice integer answers, so we can see the point of intersection very clearly. If we didn't, we'd have to go and solve it anyway to find them, x equals 2 and x equals negative 1. But now I know those points, I can answer the question, when is it below? Well, it's always below here on the left-hand side of the asymptote, so x is less than negative 2. But it's also below in between minus 1 and 2. As I say, you could use a graph to solve that. I don't think it's the most efficient way of doing it, but you could. Alright, let's look at some questions that have come from, well, this one's a very old one, 1990. They gave us the y equals square root, so the top half of the parabola, and they've also drawn some rectangles in there. You'll see why they did that in a second. Show that the graph is increasing. So again, this is the idea that, oh well, this is always increasing. Unfortunately, we can't just look at the picture and say, well look, it's going up. It's obvious. They want us to actually have some maths behind it. We know the curve's increasing when the derivative is greater than 0. That's what we know. Y equals square root of x, the derivative would be 1 on 2 root x. That is always positive. Okay, so we're saying the positive square root of x, and 1 and 2 are obviously positive numbers. So I know that's always positive. So yep, I don't know whether I really needed to do this, because technically it's only positive when x is greater than 0. So alright, I'm showing then that x equals 0, y actually does equal 0. But does it matter about the starting point? Because we're saying it's increasing, and at the starting point, well, you haven't started, so what's it matter? As soon as it goes past that, we've just proven it's going to be positive. So maybe I didn't need to do that for the starting point. But anyway, the curve is increasing for x is greater than and equal to, I've actually proven. Oh, well, that is what they asked. So I suppose we did have to check on that one. Right. Hence, go and show this inequality that the root 1 plus root 2 all the way up to root n is always greater than or equal to the integral of that curve they gave us. And nicely, we've been given the answer for that integral. It is 2/3 n root n. Mind you, it does say show that, so we may well have to do that as well. Okay, there's the graph they gave us, the picture. And this is why they drew the rectangles in. It's to give us that idea. If you remember when we looked at integration, we used the idea of outer rectangles and inner rectangles and things like that. Well, they've drawn those outer rectangles in. So what we could say is that the area of those outer rectangles, because the curve's increasing, will always be greater than or equal to the actual area under the curve. We've always got an overestimate. So therefore, the area of each of those, well, they all have a width of 1, and the first rectangle has a height of root 1, the next one has a height of root 2, and so on going up to root n. So all of that is greater than or equal to that integral, the area under the curve, that they want. So let's now go and evaluate it and show that it's 2/3 n root n. Integrate root x, we get 2/3 x root x. And going from 0 to n, substitute in, we have our answer, 2/3 n root n. Now they asked us to do an induction proof. Same pattern, but this time we're going to show it's less than or equal to something. So 4n plus 3 over 6 root n. Okay, induction. First case, n equals 1. Left hand side, that first term is the square root of 1, which is 1. right hand side we end up getting 7 on 6. But yeah, that is less than or equal to. In this case it's less than, but yeah, that is less than or equal to. It's less than. Hence the result is true for 1. We'll assume what it is we're trying to prove, and now we want to go and prove the next case, k plus 1. So this is what I am trying to prove, but again I'm using the idea of pulling everything to one side. I'm going to try and show this is always negative, or 0, less than or equal to 0. It's a series type, so I can pull out the last term and then I get my assumption there, the root 1 up to root k. I can substitute in for that. So I got to play around with this and show it's negative or 0. 0 is probably the best one, but anyway, see how we go. Common denominator is going to be 6. I've then rewritten the first fraction, you'll notice, as an entire surd, because I'm trying to get the square root of k plus 1. I'm trying to have them the same one. And the second one's already got the square root of k plus 1. Is there somehow I can get the square root of k plus 1 factorised out? So I've made it an entire surd. When I expand that out, I get 16k cubed plus 24k squared plus 9k. Well, if I divide k plus 1 into that, it doesn't go in it exactly. We have a remainder of negative 1. But I'm dealing with inequalities here, not equalities. It is fair to say that that line is less than the next line, because that second last line there, it's this minus 1. Well, if I minus something from it, it must be smaller. So it is fair to say that this second last line is actually less than the last line, because it's 1 less under the square root sign. Now remember, we're trying to prove an inequality, and as long as that inequality sign is preserved, which it is, we're only dealing with less thans here, or equal signs, that's fine. Everything's okay. But now that means I can have the square root of k plus 1 I'm looking for. I can pull these terms together, because now have a look at that second factor. 16k squared plus 8k plus 1 is a perfect square. And it happens to turn out to be 4k plus 1 squared. I can simplify the surd and look what we've got. 4k plus 1 root k plus 1 minus 4k plus 1 root k plus 1, that's 0. And that was what I was trying to get. So yes, that is what we want. Hence it is true for k plus 1 if it's true for k, and then we can induce it. And there's our inductive proof. Okay. The final part of the question then is we're going to estimate this, the square root of 1 plus the square root of 2, all the way up to the square root of 10,000. Whoa, but to the nearest 100. We have basically now trapped our series between two things. In the first part we showed it was always greater than or equal to something, and in the next part we showed it was always less than or equal to something. So it's always in between. Well, I want the series that goes up to the square root of 10,000. So if we let n equal 10,000, this must be true. Let's work out what these two end things become. The left-hand side, to the nearest 100, is 666,700. But so is the right-hand side. So if we've trapped it between these two numbers that are the same thing, then that must be what that series adds up to. So there's our answer. Okay, we're going to prove x is always greater than sine x. And I'm going to use a graph to do it. So if I draw those lines here, there's y equals x, there's y equals sine x. And again, we can't just look at the picture and go, oh look, it's always above the red curve, fantastic. We've got to put some maths behind it and explain why that's always the case. So if I just look at the line right now, I know the slope of that line is 1. Right, or I can differentiate and do it that way, or simply say, well, the slope of that line is 1, whatever. Well, let's have a look at the sine curve. When we differentiate sine, we know we get cosine. For this first section, the first quadrant, between 0 and pi on 2, well, I know the biggest the cosine curve ever gets to is 1. So I know our derivative, which is cos x, will always be less than 1. Well, that tells me that the line y equals x must increase faster than y equals sine x. Now if they start at the same point and the line is increasing faster, it must always be above it, because it's going to get steeper quicker. For x is greater than pi on 2, well, sine x is always less than or equal to 1. And so therefore, well, our line's going to keep going up. So that one, yeah, sure, x is greater than sine x, because that's always going to be the case. So yeah, x will be greater than sine x for any positive number. That will always be true. So there's a graphical way of solving that problem, which was similar to last year's HSC. X is greater than log x we had to prove. I didn't actually draw the picture this time, but I just used the calculus behind it. Function x, I pulled it to one side this time, and I've said, well, that's x minus log x. I've made it one function. Differentiated that, I get 1 or minus 1 on x. The second derivative I also found is 1 on x squared. Now I know stationary points will occur when the first derivative is equal to 0. We know that. So when we solve that, that's at the point x equals 1. Now the second derivative turns out to be 1, which is a positive number. So I know that 1, 1 is a minimum turning point. So the smallest that this can be is 1. That's the minimum turning point. There are no other stationary points. Certainly not in the domain we're talking about, x is greater than 0. So if that's the minimum point, and there are no other stationary points, this curve must always be above 1. Well, if it's above 1, it's certainly bigger than 0. So x is greater than log x. So I didn't actually draw the picture, but I used the calculus tools that we would use if we were to go and draw it to go and prove this question. It then became a really interesting inequality question. I think we actually looked at it last year, if I remember, but just to remind you what it was. Using part 1 or otherwise, proved this interesting inequality. E to the power of n squared plus n is greater than n factorial squared. Well, they've said using part 1 or otherwise. Well, it probably makes sense to use part 1. Otherwise, why are you giving me this hint? So that is what I'll start with. I'm going to start with something I know to be true. We proved x was greater than log x. Well, I'm just using n because that's the pronumeral they've got. So n must be greater than log n. And just to let the person looking at my solution know, hey, I've taken that from part 1. That's what we did in part 1. Okay. Got to get to this equation. But it also means that n minus 1 must be greater than the log of n minus 1. I can replace n with anything I like, as long as it's a positive number. N minus 2 must be greater than the log of n minus 2, and so on and so on and so on. I can keep going down until I get to 1. 1 must be greater than log 1. Because all of those inequality signs are running in the same direction, I can add those together, the inequality is preserved. So the left-hand side and the right-hand side, I get these two series of numbers. But on the left-hand side, notice that actually is an arithmetic series. Okay, first term's 1, the common difference is also 1. We're just going up by 1s. So on the left-hand side, I could just sub that into my formula for an arithmetic series. So we get n on 2, n plus 1. The right-hand side, I can use my log laws. When we add logs, we multiply. So I'll get the log of n times n minus 1. Why do that? Because, well, n factorial is, of course, n times n minus 1 times n. It gets the factorial in there. So now I know that, well, I've multiplied both sides by 2, that n outside of n plus 1 must be greater than 2 times the log of n factorial. Now I can get the n factorial squared, because we have a log law that says, boom, bring it in. There we go. Oh, that is very close. Look at what we've got. N squared plus n, I've expanded the left-hand side out. That is the power that they want. And we have the log of what we want. So I have it. For want of a better word, exponentialize both sides. I've applied the exponential, and I can do that because I know e to the power of x, if you think of that curve, is continually increasing. And that's what I've been saying. If you know the piece of the curve you're interested in is continually increasing, you can apply that function to your inequality and the inequality will be preserved. Now in this case, it's always increasing. It doesn't matter about the piece we're looking at for the exponent, it's always, this is not a problem. And so there's the result that they want. Alrighty, and just a couple more questions we'll add there.